All right. Hi, everyone. Thank you for the introduction. My talk today is on how to model variables in stream networks in space and time. So assessing water quality in rivers is required in many countries, as you probably know, including Australia. These days, we have sensors, in-situ sensors, which allow us to obtain water quality variables almost in real time. So these sensors are normally placed in the branching network, and they record multiple parameters, including temperature, pH, nitrate, etc. But how do we establish space-time dependence with this sort of data? So in this figure, what we observe here in, for example, in this location 1, is closely related to what we measure in location 2, 3, and possibly 4. So therefore, for modeling in branching networks, we have to account for spatial dependence using stream distance, but also using flow connectivity. This is the same representation of the network, but in this case, across time. So let's say that we want to estimate what happened in spatial location S3 at time 3, and it's going to be conditional on what happened at the same spatial location in previous time points, let's say T1 and T2, but also on what happened on the neighboring sites. So in this work, we propose the following dynamic model in which a variable y in space and time is a function of a design matrix of some covariates, plus this bit here, z in S and T, which is composed by two parts. So the first one is the vector autoregression, which is composed by multiple time series. And the second part, W in S and T, is how we incorporate the spatial dependence. So in the first part, this phi on here is a transition matrix, and is going to determine how much temporal dependence we have in our model. So but one of the complications with this model is the amount of parameters when we have a lot of spatial locations. So we try a lot of variations of that transition matrix, from a very simple one, like in case 1, to a more complex one in case 3, in which we borrow across time from the nearest neighbors. So now that we have incorporated temporal dependence, so we incorporate spatial dependence using so-called tail up and tail down covariance structures, which depend on flow connectivity and stream distance. So to assess how well these models perform with real data, we use the following case study of mean daily temperature waters in the northwestern part of the United States. With it's a really large branching network with extending over 50,000 kilometers. We have 220 spatial locations on there, and we have time series data from more than 5 years. And so the aim of this model on this case study is to estimate the missing values here on gray, but also make predictions across the whole branching network. Right? So we use the following covariates. So for example, we consider a stream slope, the elevation, the drainage area, the air temperature. And we try, as usual, we split our data set into training and testing. And then we assess the out-of-sample prediction in our testing data set. So we try a lot of combinations of spatial and temporal structures. And in all of these combinations, we found that the model performs really well. So the root mean square error is between 0.5 to 0.84, which is substantially smaller compared to some others published in the literature, excuse me. So how are the predictions? So in the held out 20% of the data set, we compare the true latent temperature with what we estimate from the model. And we see on here that they are really similar. So meaning that the model is producing really good predictions. Some output from the model as well is that we can predict across the whole branching network. This is, for example, the estimation of the temperature in 4 different dates in the time series. All right, from the practical point of view, ecologists are interested, for example, in the probability of exceeding certain threshold. In these branching networks, we can find species such as bull trout, and lab studies have found that for bull trout, for juvenile bull trouts, when the temperatures exceed 13 degrees, produces thermal stress on the fish. Therefore, identifying those segments and those dates in which the temperature exceeds this limit is critical. Some of the possible interventions in this case are, for example, planting trees in the riparian zone, which reduce temperature. And some other authors have reported that introducing beavers in some of these segments, these beavers tend to produce artificial dams, increasing the water volume and reducing also the temperature. All right, so from the model, we then obtain for each of the time points the probability of exceeding that threshold of 13 degrees. In this representation, we have the hottest day of the year, and these yellow areas here are those with probability almost 1 of exceeding that threshold. So with a model, we can obtain those segments with a really large probability of exceeding the limits. Right. Well, summing up, so far we have found that these models produce suitable estimates and really good predictions. We have found that they outperform some models that we find in the literature. As a future work, we are working on the implementation of separable space-time models, some other covariance structures to account for space and time dependence. And as part of future work as well, we are working with the Department of Environment and Science here in Queensland, and they are deploying, or they are going to deploy a lot of sensors in Queensland rivers, which will allow to obtain like a lot of data, therefore, for water quality and anomaly detection. I would like to thank all my collaborators in this project, scientists on there, and thank you for your attention.